All right, this will be the video on current and current density. So we're going to talk about basics of current all the way up through resistivity and conductivity. We'll end this video there, and then we'll pick it up again talking about Ohm's law and resistance in the next video, and talking about basics of circuits next video. So this video is going to be all about you have a wire, and we're going to keep track of the particles that are actually moving in the wire. And we want to talk about circuits. We're going to be talking about metals or conductors. So we're especially going to focus on conductors where there's free charge carriers that are free to roam around. And in metals, the charge carriers are electrons. So as depicted here, there's sort of like a lattice of positively charged ions. And the electrons are whizzing around here, and they're moving really fast. So hundreds of meters per second. So they're traveling like close to the speed of sound or something, you know, very, 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 very fast. But they're just kind of zigzagging around in random directions, unless you apply a potential difference. So we'll talk a little bit more about this later in the video. But if this side is at a different potential than this side, then there's a tendency for the electrons to drift from one side to the other. And the speed that they drift is different. So we label this with drift speed, V sub D. The drift speed is different than how fast they're just whizzing around real fast. For a formula for how, so the proof of this formula is we're keeping track of a section of the wire and let's suppose that these electrons are all moving to the right. So in this section of wire of length delta x, it'll pass through this area. We can relate delta x, the area of the wire, so that's volume. The electron electron density. So this electron density n subscript e in this formula, this is describing the number of free charge carriers per unit volume there are. So for aluminum, there are 6 times 10 to the 28 free electrons that are free to move around within the metal per cubic meter, right? And so there's a different value for each of these metals. So this electron current density, so this I sub e, this is the number of electrons per second. So this doesn't have dimensions or units or anything. So this is just 1/seconds, number of electrons per second. This is how many are passing through a cross section of the wire. So if like you have the wire and I put my hand here, it's keeping track of how many electrons per second are passing through my hand. That's the I sub e. It's not quite current. Later on, in this video, we'll talk about current, and that'll be charge per second. This is number of electrons per second, or maybe number current, electron number current. So electron number current is related to, well, how many electrons you have. It's related to the cross-sectional area of the wire. It's also related to this thing called the drift speed. So if you plug in like the area of a typical wire, a typical electron density, so one of these numbers, and a typical actual value for the number current, so we can measure that. We can measure current and then backtrack and think of what this is. The actual values for V subscript D are very, very, very small. So you'll notice, like in this problem, we have 1 times 10 to the minus 4 meters per second. Really, really small. So this is, you know, less than a millimeter per second. So they're zigging around like this, and they're very slowly just sort of drifting to one side. But there's so many of them that can still have an appreciable current that's going through any one cross section. Okay. So actually, when you turn on the light switch to turn a room light on, an electron from over here isn't going all that distance. So when you turn this on, you're creating an electric field. You're creating a potential difference between the two sides, and all the charges just sort of scoot over a little bit, all at the same time. And they're scooting over very, very slow on average, but there's so many of them that can still have a big effect on the current, and, you know, noticeable effect on light switches and all that. Okay, so we're largely going to skip this section, creating a current. There are 2 main points to this. So first of all, the reason charges move is because there's a non-zero electric field in the wire. So everything that we've talked about before says that I realize now that I'm saying we're skipping this section, but I still wanted to highlight some main things about it. There's no formulas from this question, from this section, I guess I should say. So before we were saying that the electric field is 0 inside a conductor. That's true in equilibrium. But we're now going to look at current, which is a non-equilibrium situation. There is an electric field set up in the wire. And that happens because of, so your book explains this via a simple model where it's saying that charges on the edge of the wire are sustaining this electric field that's going to exist within the wire and scoot the charges along. I don't want to get into this too much, which is why we're skipping this section, but that's one of the points it's trying to make at the beginning. And the second one, they're trying to be a little quantitative with a simple model. So keeping track of how long does it take before an electron hits an ion and scatters in a random direction, and how that relates to electric field and all that. So we're not going to need that formula. That one's not too important for us. Okay, so what will be more important here is current. So we were talking before about electron number current. But normally we just say the word current, and current is how much actual charge is passing through that cross section. So the current, I, is charge per unit time. So remember, we measure this in coulombs. So measure charge in coulomb, measure time in seconds. And 1 coulomb per second is an amp, AMP. 1 ampere, or or we also write AMP. This is the SI unit of current. And 1 amp is actually pretty big. Like most of the currents, I guess you can have a 1 amp current, but that's something pretty big. Like if your toaster's on, then you have a few amps for the current. Most small electronics are more like milliamps. And this current is related to the electron number current by, well, it's the number of electrons times the charge of each electron. That tells you how much charge is going through each second. So this formula probably hopefully is not too surprising. One comment about the sign, about the directions. So you can blame Ben Franklin for this. He just kind of randomly assigned negative versus positive. And if he knew then what we know now, he probably would have done the opposite convention. So electrons are negatively charged. If they move to the right, like in this picture, if negative charge moves to the right, the overall flow of positive charge is to the left. So we're going to define the direction of I. So in this wire, the current is the whole cross section. So we're describing the current just along the wire. Is it to the left along this wire or to the right along the wire? And it's the direction that positive charges are flowing. So if positive charges are actually the ones moving, the current is the same direction that the positive charges are moving. If the electrons are moving this way, then the current is going to the left. Okay, so kind of an annoying technical issue. So electrons moving one way, current going the opposite way. And almost always when we draw circuit diagrams, we're just going to assume that the charge carriers are positive. So we actually don't get into a lot of trouble just assuming that these charge carriers are positive and going one direction with the current rather than the actual electrons going the opposite way. We can still calculate everything just fine doing that. Current density. Okay, so I was saying before that the current is describing the entire wire. So the current is all the charges that are passing through an entire cross section. So this whole thing is the current. Current is the amount of charge passing through this entire thing. But sometimes we want to look, and we're going to have an equation in a second that wants to look a little bit more locally, like what's going on at that point. At that point, charges are moving. And again, let's assume that the current is to the right and that positive charges are moving to the right, just so we don't have this annoying technical issue. So what's going on here is that we have a bunch of little tiny currents. And what we like to do is describe the current per unit area. So there's current I, which is the total charge going through the entire wire. And then there's these, you could actually break this up into the current per unit area. So if you look at a tiny piece of area in that cross section, you can keep track locally of what the current density is along the wire. So is there more current going on in the center of the wire or towards the edges? well, you could have a different J value in the center of the wire versus along the edges. If the current is spread out evenly over the wire, then you can just take the whole current of the entire wire divided by the area of that wire, pi r squared, right? This is the cross-sectional area. And there's a formula for current density in terms of these quantities that we've seen before. So the electron concentration, number per unit volume, the charge of an electron, and the drift speed. And notice how normally this formula, if this was a formula for I, this would have an area on the right. But to get rid of that area, to talk about a quantity that's independent of area, we can divide by area, and that's why current density is a little nicer there. So if we knew, well, so this formula is just like solving for drift velocity, assuming we knew everything else. So if you knew the current density, the number density of charge carriers, then you could solve for V sub D. And again, you get a really small value. Okay, current. So the point of this section is Kirchhoffs' junction law, which we'll get to at the bottom there. The point here is that current is not used up. Okay, charges don't build up on this bulb. Whatever current is flowing here is the same amount flowing here, is the same amount flowing. Whatever flow is flowing into bulb A is leaving bulb A at the same time. There's no charge that congregates in bulb A. Right? Charges aren't destroyed there, they're not created there. Just charges are flowing in and flowing out. And the bulb doesn't pick up a net charge over time. It's always neutral. So however much charge is entering it is leaving it. We'll look later at power. So it's the fact that charge is going through the bulb that makes it light up. We'll talk about that later. But right now, what's important is that whatever's entering is leaving each device. And so the current everywhere is the same. Right? The current in this loop, unless there's a junction, unless there's a splitting of the wire, then the current is constant. And your book uses an analogy with water here. So like the water flow here, even if it's being used to turn a turbine, whatever water is entering here is leaving here, even if it's doing some work on some, even if it's generating some power. And this is due to conservation of charge, and you can keep track of currents going into a junction and out of a junction. So again, charge doesn't build up right here. So however much current is entering there is how much is leaving here. So if this was I1 and this was I2, both of them entering, then it would equal I3. Right, the amount leaving. So the exact equation that you would set up depends on the picture that you have, but the current in is equal to the current out. Last section here, conductivity and resistivity. So one reason we like talking about current density J is that it's a local quantity. So right here, charges will want to move to the right, and there's how quickly they're going is described by this current density J. But what's the reason for it? Why do charges want to go in that direction? Well, if plus charges are moving in this direction, it's because there's a higher potential here than here. Right? There's an electric field set up to the right. So there's a cause. So the electric field is the cause. You set up a potential difference, maybe by connecting the two ends of the wire to a battery. And the effect is the charges moving. How much they move is described by the current density, is the J. So there's a cause, and that's the effect, and there's a constant proportionality. So it turns out that if you double the electric field, you'll double the current density at points in space. If it's doubled everywhere, then you're doubling the overall current as well. This constant proportionality is called the conductivity. And it's describing how easily how easily you can set up a current in a device or in a material. So like for copper, pretend you set up an electric field of 100 volts per meter. So you're setting that up in a bunch of different materials. For copper, you can get a really big current based on that. It has a really high conductivity. For insulators, or for nonmetals, you set up the same electric field and you hardly get any current at all. They have really low values of conductivity. So your book tabulates some of these values mostly for conductors, just because for insulators, this value is so small. And we're not, normally if we're trying to get charges to move, we'll look at conductors rather than insulators, because insulators aren't really good at doing that. So copper is one of the best ones here. Gold has a better value of, well, not conductivity, but gold is nice for other reasons, but copper is relatively cheap and good value of conductivity. So a lot of these wires are made of copper. Silver is a little bit better, but more expensive. So there's another quantity called the resistivity, and this is just the inverse of the conductivity. When we talk about resistance, it's more closely related to this quantity resistivity. So this is just the inverse. The better conductor something is, the lower resistivity it has. So like I was saying before, copper has a big value of conductivity, it has a small value of resistivity. We're going to talk about this SI unit later. So I just want you to know that these are SI units. We'll talk about what this unit is next video. It's ohms, and it'll be the unit of resistance. So we're going to use resistance more often than resistivity. So we'll hold off on it, but just these are the SI units of these quantities. Okay, superconductivity. So actually the conductivity goes to infinity for some special materials at really cold temperatures. So you can plot, like, as a function of temperature, what the conductivity is. It's some value, and then it just diverges at some special temperature. And for these materials, the conductivity goes to infinity, the resistivity goes to 0. They basically have 0 resistance. They can sustain currents, and they can do funny things, like you can levitate magnets. You can see it's pretty cold because they made it really cold for this to occur. This is called superconductivity, and a big research area is to find superconducting materials, but at temperatures closer to room temperature, so you don't have to waste a lot of energy trying to cool it down. Waste a lot of, like, liquid helium or stuff that has limited in resources. Okay, so let's look at this example problem. This touches on a lot of the quantities that we've seen in this video. An aluminum wire where the radius is going to change. So here you're given the diameters, and what's going to be relevant for us are the areas. So I'm just saying that in region 1, which it's the same down here as up here. In region 1, we have a radius that's half of this value, and the cross-sectional area is pi r squared. So there's some area A1, there's some area A2, and there's a conductivity value for aluminum, and that's constant for, that's just a constant for aluminum. Like the conductivity here and the conductivity here are the same. So there's some constant value. You would look it up in a table, and it's this value. Right, so I'm going to write answers in terms of these 3 quantities, areas and the conductivity. And these are the numbers that we would plug in. Okay, so what's the current in the 2 different regions? Well, it looks like 10 amps is what's going in. And so the current is 10 amps downwards everywhere. Downwards everywhere, whether it's in region 1 or in region 2. This is everywhere. Regions 1 or 2. The current density, though, that is what's going to change. So you have the same current that's spread out over either a big area or a small area. So the current density in region 1 is the current divided by A1, and current density in region 2 is that same current divided by A2. And because A2 is less than A1, this tells us J2 is greater than J1. And it looks like it's half the radius. The region 2 has half the radius of region 1, and so it's 1/4 the area. And it's actually 4 times the current density. So you should see that J2 is actually 4 times J1. So if you plug in numbers, you really only have to plug in numbers for one of them, and then the second one you know right away from this. What about the electric field? Well, the electric field is related to the current density. This is a formula that I skipped over, and I should not have. Well, I pointed to the things in this formula, but I guess to stress its importance, J equals sigma E. So we can solve for, if we know one of these 2 things, we can solve for the other one. What's the electric field in these 2? Well, going back to the problem here on the left, it looks like if J2 is 4 times bigger than J1, then the electric field there is also 4 times bigger, right? The sigma is the same for the 2. So it looks like E1 is equal to J1 over sigma. So you can plug in numbers there. And then E2 is J2 over sigma. And it looks like this is 4 times E1. So the electric field's stronger here. E2, it's getting pretty messy. E2 is some value, and then E1 is a smaller electric field, E1. Right, so we're able to infer some information about the electric field just based on the, what's going on with the wire's radius. Drift velocity. So we have another formula for drift velocity. So we have to go back to where we were talking about that. It looks like we had drift velocity right here. So drift velocity in general is J over N E times the charge, E. So this is some value. So this is constant for aluminum. So you would have to look up that value, the number density for aluminum. This is the charge of an electron. So you'd plug in 1.6 times 10 to the minus 19 coulombs for this. And then this is a different value for 1 or 2, region 1 or 2. So it looks like the bigger the current density, the bigger the drift speed. So J2 is 4 times bigger. It looks like electrons on average are drifting downwards 4 times faster here than here. And for electron current I, remember there was the difference between, so this was the number of electrons per second going through a whole cross section. This we just need to multiply by the charge of an electron to get the total current. And this is a constant 10 amps here. So it looks like I sub E is the same everywhere in this problem. It's the 10 amps divided by the charge of an electron, 1.6 times 10 to the minus 19 coulombs. So if you're dividing by a really small number, 10 to the minus 19, you have a lot of electrons per second passing through any one cross section. So whether you look at a cross section here or a cross section here, there's the same number of electrons per unit time that are passing through either of those 2 cross sections. Okay.